Hi everyone! In the previous courses, we introduced the BGP L3 VPN, EVPN L3 VPN, and EVPN VPLS. This course focuses on the EVPN VPLS over SRv6 TE policy scenario. Virtual private LAN services are used to provide point-to-multipoint L2 VPN services. The figure on the left shows a typical example of VPLS networking. We can see that the intermediate Layer 3 IP network simulates a Layer 2 switch to which CEs are connected. The figure on the right shows the logical implementation of a VPLS network. Let's still take an example of 5 devices to describe the detailed configuration and verification processes in this scenario. P1, the P, and P2 all reside on the public network. C1 and C2 are connected to customer networks. A bidirectional SRv6 TE policy needs to be established between P1 and P2 to carry EVPN VPLS. The configuration roadmap is as follows. First, enable ECs on P1, the P, and the P2 to achieve basic route reachability. Second, configure an SRv6 TE policy between P1 and P2. Third, configure CE access on P1 and P2. In addition, establish a BGP EVPN peer relationship between P1 and P2 to transmit VPLS information between the PEs. For ease of understanding, we'll obtain packet headers from the two interfaces of P1 for packet parsing. Because EC's configuration methods are practically the same across all SRv6 TE policy scenarios, they will not be described in detail. Basic SRv6 configuration involves the following steps. First, enable SRv6 globally. Second, configure a source address for IPv6 packet encapsulation. Using the IPv6 addresses of the loopback interfaces is recommended. Third, configure locators. The EVPN VPLS scenario requires a multicast locator and a unicast locator. Because there are two locators configured, we need to run the two corresponding commands in the EC's view to advertise locator routes. Note that P1 and P2 both require two locators, but the P requires only one. After SRv6 is successfully configured, ECS advertises SRv6 locator routes through LSPs. Now let's take a closer look at the format of an ECS LSP carrying SRv6 information. We can see that the ECS LSP carries two pieces of locator information, and two locator routes are advertised, including one unicast route and one bomb route. The ECS routing table on P1 contains 5 locator routes. According to the ECS routing table on the P, we can see that the P has also learned SRv6 locator routes even though it is not enabled with SRv6. As such, the P can also correctly forward SRv6 packets after receiving them. This explains why SRv6 capable devices can be deployed together with common IPv6 devices. Next, let's take a look at the SRv6 TE policy configuration. Because the configuration methods are practically the same across all SRv6 TE policy scenarios, they will not be described in detail. After configuring ECS and SRv6, let's check the SRv6 TE policy connectivity. If the connectivity is normal, we can then configure BGP. We need to configure CE access on the PEs and specify seeds for BDs. First, let's see how to configure the CEs. Typically, we need to configure the CE interface connected to a PE as a trunk interface, and the CE interface connected to a host as an access interface, and then add the two interfaces to the same VLAN. However, to facilitate subsequent inter-CE packet forwarding verification, we configure a VLAN.1Q sub-interface on the CEs, specify the VLAN ID of 10, and configure an IP address. Moving on, let's see how to configure the PEs. The first step involves creating an EVPN instance working in BD or common mode. The second step involves creating a BD and binding an EVPN instance to it, so that EVPN VPLS data is forwarded within the BD. The third step is to create a sub-interface and connect the PE to the corresponding CE through the sub-interface. In addition, specify a LAN ID, which is the same as that specified on CE, and add the subinterface to the BD. We can also create multiple subinterfaces and add them to the same BD. Finally, we need to run the opcode and the DT2U and opcode and the DT2M commands to configure a unicast seed and a bomb seed, respectively, for the BD under the locator. Next, let's switch our focus to the seed tables generated on the PEs. In the local seed table on PE1, we can see a unicast seed of the DT2U type and a bomb seed of the DT2M type. Each SRv6 seed is bound to a BD. The PEs can associate the SRv6 seeds carried in packets with locally configured BDs and forward the packets in the BDs. Now we need to establish a BGP EVPN peer relationship between the PEs to transmit routing information between the CEs. The key configurations are as follows. First, we need to establish a BGP EVPN peer relationship. The commands to be run in the BGP view and the involved views are the same as those in the EVPN VPLS scenario, indicating that EVPN VPLS and EVPN VPLS share the same EVPN peer relationship. Then we need to configure root recursion. The two commands are similar to those in the EVPN VPLS scenario, but the involved views are different from those in the EVPN VPLS scenario. In addition, because the EVPN VPLS scenario requires two locators, that is, one bomb locator and one unicast locator, we need to specify two locators here. The final step involves configuring an EVPN source address for the corresponding PE. The configurations on PE2 are similar. Following that, we need to configure root coloring on the PEs. Then we need to configure and apply a tunnel policy. These configurations are similar to those in the EVPN VPLS scenario and therefore will not be described in detail. After a BGP EVPN peer relationship is established, the devices exchange update messages to advertise EVPN VPLS routes. Next, let's look at the BGP update message format. The EVPN VPLS scenario involves two types of update messages. A unicast update message carries common path attributes, such as the BGP prefix seed attribute, which carries an n.dt2u seed. The EVPN NLRI shows that the main address family identifier is L2 VPN, the sub-address family identifier is EVPN, and the next hop is the address of P2. In addition, the route is a Type 2 MAC advertisement route. According to the detailed route information, the route carries an RD and CE2's MAC address. In contrast to unicast update messages, BGP update messages with bomb and .dt2m seeds carry the PMSI attribute, containing tunnel type, label, and destination address information. This attribute is mainly used for bomb traffic forwarding. The BGP prefix seed attribute carries an n.dt2m seed. The NLRI shows that the route is a Type 3 inclusive multicast route carrying an RD. Because a broadcast MAC address is used for packet forwarding in bomb scenarios, no specific MAC address is carried here. Now let's look at a BGP EVPN routing table generated based on BGP update messages. Take P1 as an example. The command output shows Type 2 MAC advertisement routes and Type 3 inclusive multicast routes. Observing the Type 2 MAC routes details, we can see that the route carries a range of information, including the RD, next hop, RT, seed, and specific MAC address. According to the Type 3 inclusive multicast route details, the route carries the PMSI attribute in addition to RD, next hop, RT, seed, and PMSI information. Let's move on and check the ARP information on CE1. The command output shows that CE1 has learned CE2's ARP information. And when we run the ping command on CE1 to ping CE2, the ping is successful, indicating that the configuration has succeeded. The TTL value is 255, which is the same as that in the EVPN VPLS scenario. This indicates that a virtual direct link is actually established between C1 and C2. That's all about the implementation of EVPN VPLS over SRv6 TE policy in the control plane. Next, let's look at the forwarding plan implementation. Assume that we initiate a ping from C1 to C2 and obtain packet headers on this interface of P1. We can see that ICMP encapsulation is first performed on the original data, followed by IPv4 encapsulation, in which the source address is the address of C1 and the destination address is the address of C2. Then VLAN.1Q encapsulation is performed, and the encapsulated VLAN tag is 10. Finally, Layer 2 Ethernet encapsulation is performed. After P1 receives the packet from this interface, it removes the VLAN tag, performs SRv6 encapsulation for the remaining packet data, and sends the packet to P2. Looking at the encapsulation of this packet, we can see that only simple IPv6 encapsulation has been performed, using the piece and.exceed as the destination address. The packet carries an SRh, which consists of SRv6 TE policy and n.dt2useed information. In EVPN VPLS scenarios, the public network transparently transmits CE data. After receiving the ping request, C2 sends a reply packet to C1. The packet then reaches P1 through P2. For this packet, the source address is the address of P2 and the destination address is the n.dt2useed configured on P1. Because the packet is transparently transmitted, its original data is carried here. After receiving the packet, P1 removes the SRv6 encapsulation and then sends the packet to C1. Finally, let's summarize the information transmission and data forwarding processes in an EVPN VPLS over SRv6 TE policy scenario. Let's first look at the ARP information transmission process in the control plane. We need to establish an AC connection between each CE and PE, and configure a BD to which multiple subinterfaces associated with the CE are added. The BD needs to be bound to an EVPN instance. The corresponding routing information enters both the routing table of the EVPN instance and the EVPN routing table. EVPN routes, including Type 2 MAC advertisement routes and Type 3 inclusive multicast routes, are transmitted through the EVPN peer relationship between the PEs. After the communication channel on the public network is established, the CEs learn each other's ARP information through ARP requests and generate ARP entries. Moving on, let's look at the data forwarding process. The process of data forwarding from C1 to C2 is as follows. First, C1 sends the original IPv4 packet encapsulated with a VLAN tag to P1 through the interface bound to the corresponding BD. Second, P1 finds the associated BD and next hop information according to the VLAN.1Q information in the packet, and encapsulates an SRh and n.dt2useed into the packet. In the forwarding phase, according to the instruction bound to the first n.exceed, P1 decrements the SL value by when, changes the destination address to this address, and then forwards the packet through the outbound interface bound to the n.exceed. Third, the P searches the local seed table according to the outer destination address and finds a matching n.exceed. According to the instruction bound to the second n.exceed, the P decrements the SL value by when, changes the destination address to this address, and then forwards the packet through the outbound interface bound to the n.exceed. Fourth, P2 searches the local seed table according to the outer destination address and finds a matching n.dt2useed. As instructed by the n.dt2useed, P2 removes the IPv6 header, finds the matching BD, and forwards the packet to other AC interfaces in the BD. That's all for this course on EVPN VPLS over SRv6 TE policy. Thank you for watching.